Implicit differentiation is what we're going to cover today, and anytime you see this word implicit, you are thinking of an expression that has both x's and y's in it. Anytime you see the word implicit as it relates to derivatives, you're thinking about an expression that has both x's and y's. And the best way we can do this is just get right to some examples. Let's say that you are asked to find the derivative of y squared equals x. The only thing that you have to do differently here, what we're going to do is we're actually going to do the derivative of both the y terms and the x terms, but there's a little wrinkle, okay? If I do the derivative of y squared, pretend it was an x, what would its derivative be? It would be 2y. But here's the wrinkle, is we call this 2y times, we kind of think of it in like a chain rule type deal. We think of it's 2y times the derivative of y with respect to x. And that's the wrinkle, is anytime you do the derivative of the y term, you have to multiply it by a dy dx. On the other side, what's the derivative of x? 1. Okay? And you've already seen the new wrinkle. Now, to finish this, all we have to do is solve for dy dx. And that, yeah, it is going to be the derivative of this implicit expression. Okay? Anytime we have y's and x's, then this is called an implicit expression. So what we're going to do now is do a little bit of algebra. We're going to come over here, and I'm going to take 2y dy dx, and I'm going to solve it for dy dx. So can't I divide both sides by 2y? And dy dx, in this case, equals 1 over 2y. I suppose you could write that as 2y to the negative 1, but you don't have to. Let's do another problem. Let's find the slope of the circle x squared plus y squared equals 25 at the point 3, negative 4. Now, I think I have my young budding AP calculus stars trained well enough to know that if you see slope, what are we thinking? I need to find the derivative. Okay? So, but what am I finding the derivative of? Well, I'm finding the derivative of x squared plus y squared equals 25. And lo and behold, it is an implicit expression. Okay? The equation of a circle is an implicit expression. So, let's find its derivative. Okay? Let's find the derivative of this. So, the derivative of x squared is 2x, that's easy, plus the derivative of y squared, which is 2y times dy dx, equals, what's the derivative of 25? 0. Okay, so what did we do on the last problem? Didn't we solve for dy dx? We're going to do that again. So I'm going to subtract 2x from both sides, and I'll have 2y dy dx equals negative 2x. Then I need to divide both sides by 2y. And I have that dy dx equals negative x over y, because the 2's cancel. Well, what have we learned? The derivative is also called the slope function, isn't it? So guess what? The hard part of this is done. Don't I have a function that will tell me the slope anywhere? And wasn't I given a point? So all I have to do is plug it in. All right? So the slope, m, is going to be negative x over y, and I'm going to plug in this point. So that will be the negative of 3 over negative 4, so it will be 3/4. Okay? And we did all of that using implicit differentiation. Okay? Next. Find the tangent and normal lines to the ellipse. An ellipse is kind of an elongated circle. X squared minus xy plus y squared equals 7 at the point -1, 2. Now, this is a good problem for us to do because it introduces a situation that we haven't seen yet with implicit differentiation, which is the product rule. Okay? So, follow along with me. Since I'm finding a tangent line, I know I'm going to have to do the derivative. Let's just get to it. The derivative of x squared is 2x. Minus, do you see that this is a product? X times y. I've tried to teach you that anytime you see a product, we have to use the product rule. So I'm going to put a bracket right here. Okay? And I'm going to do the product rule. The derivative of the first times the second the way it is, plus the derivative of the second, which is a y. So the derivative of the second is going to be 1 times dy dx. So I'm just going to put a dy dx. That is the derivative of the second. Times the first the way it is. Okay? And I've done the product rule for that middle term. Plus, the derivative of y squared is 2y times dy dx equals 0. And that's what I really wanted to, that's really why I wanted to go over this one, is because I wanted you to see how to use the product rule. The process from here is still the same. What am I going to do now? Solve for dy dx. So we've got some algebra to do. 2x minus y minus x dy dx plus 2y dy dx equals 0. So if it were me, I'd get the dy dx's on one side. I'll just leave them on this side and I'll take these two over. Subtract 2x, add y. Subtract 2x, add y. And now what I've got on the left side is just, use a different color, just this thing right here. So I can factor out a dy dx. If I factor out a dy dx, then I'm left with negative x plus 2y equals negative 2x plus y. And by doing that, I kind of saved myself some writing. And to finish solving, I divide both sides by this expression, negative x plus 2y, divided by negative x plus 2y, and we've got it. Okay, there's my derivative of that implicit expression. I'd leave it like that. Okay, remember what that is. That is my slope function, right? So now if I want to find the tangent line, don't I have to find the slope first? Right? So I'm going to use this function to find the slope. So m equals, what point do I have? -1, 2. So it's going to be -2 times -1 plus whatever y is, which is 2, all over the opposite of -1, which will be 1, plus 2 times 2. So that's going to be 2 plus 2 on top. That'll be 4. On bottom, it's going to be 1 plus 4, which is 5. My slope is 4/5. Now, from this point on, don't we know what to do? If I want to find the equation of the tangent line, what would I do next? Wouldn't I plug in this slope into y minus y1 equals m times x minus x1? Wouldn't that be next? Because I have a point and a slope, right? So I'm not going to finish that problem because we know how to do that, and that's basic algebra. I'd rather do a little bit more calculus. One more. What if this, on this last example, I have this expression, 2x cubed minus 3y squared equals 8. And I'm asked to find, and they give you this little notation. What does that mean? I think I've taught you what that means. You may have forgotten. That's the second derivative. Okay, if they write d squared y over dx squared, you need to think second deriv. Okay? So, rock and roll, here we go. I need to find the derivative. I need to find the first derivative. So, this is going to be 6x squared minus 6y dy dx equals 0. All right, so that's going to subtract 6x squared, subtract 6x squared, negative 6y dy dx equals negative 6x squared. Divide both sides by negative 6y. And I have that the first derivative is x squared over y. Well, that's the first derivative. We're supposed to find the second derivative. So guess what we got to do? The derivative of the derivative. New page. If I have x squared over y and I want to find the derivative of it, isn't that a quotient? Yes. So I must use the quotient rule. So the derivative of the top is 2x times the bottom the way it is, minus the derivative of the bottom, which is dy dx, times the top the way it is, all over the bottom squared. Okay? Now I want you to notice something. Don't I have a dy dx in there? Right here? Right? Well, don't I know what dy dx is? Isn't it that? Didn't we just find out what dy dx was? We found the first derivative. So guess what you have to do? You have to put that little thing in right there, that x squared over y. So now I have 2xy minus x squared over y times x squared all over y squared. And when you simplify that thing, you'll have your answer. So let's see if we can't clean it up a little bit. I'm going to have 2xy minus x to the fourth over y all over y squared. And I've got that kind of complex fraction there. What I would do is I'd multiply the top and bottom by y. That's a form of 1. I'm allowed to do that. And when I multiply through by y, I wind up with 2x y squared minus x to the fourth all over y cubed. And that is my second derivative. Okay? With the funny notation. d squared y over dx squared. That would be the second derivative. Okay? One last thing is, and I'm not going to go all the way through this one, I just want to talk about the instructions. Show that dy dx is defined at every point on the graph of f. I'm sorry, on the graph of 2y equals x squared plus sine y. Okay? Now, what you're going to do on this problem is you're going to have to find the derivative. Okay? And you see that it's got x's and y's in it. By the way, we wouldn't have a problem with this sine y, would we? What's the derivative of sine? Cosine. So when you did the derivative of this, it would be cosine y times dy dx. Okay, so that shouldn't worry us any. But I'm not going to do the whole derivative problem. I'm just going to tell you what the answer is. If I do this, I'm going to get 2x over 2 minus cosine of y. Okay. Would you agree that the only place where this thing could be undefined, look at this denominator. I can't have a 0 in the denominator, can I? So what would the cosine of y have to be? 2. Wouldn't it have to be 2? Is that possible?
I'm sure.
Is it possible for the cosine graph to be any more than 1? Remember? Now I'm talking about the parent function because that's all we had there. Doesn't it always stay between 1 and -1? Okay, so what we have shown is we have shown that it's defined everywhere because there is no place, this is impossible. I cannot have the cosine of something equal to 2. So what did I do on that problem? I found the derivative. Okay, this thing right here is dy dx. I didn't do the steps on that, but I found the derivative. And then I looked to see where could this thing be undefined. Well, cosine would have to be equal to 2, and that can't happen. And we're going to stop there for today.
So